deciding, it could be a sample size 5. All of the samples have to be sample size 5. It could be a sample size of 50. All of the samples will be 50. If I'm using this classroom as my population, maybe my sample size would be 5 or 6. If I'm going to do 20, I might as well do the whole 24. But if you're talking all the people in the United States that have iPhones, then you're talking, well, give me a sample size of maybe 300, 200, because you're dealing with millions of people. So we do a number of samples of the same sample size. And from that, we take the mean of all of those. Your sampling distribution of sample means is what we call this. If the sample statistic is your sample mean. And we write it like this. There's your sample mean. That's what we're usually going to say. Okay, now, do you see in the bottom they show a little Venn diagram? I don't have the Venn diagram. But you see the Venn diagram? Those are taking samples of the same size and finding each mean. So they took 5 samples altogether, and they found the means. Do you see why some of them overlap? Because you can use the same object in another sample. Like say I randomly sample 5 people from this group. Then I throw you all back in. I randomly sample another 5 people. Then I throw you back in. I randomly sample another 5. I can get the same person in every sample, can I? Yeah. And I can still not get one person in every sample. So that's the concept of your Venn diagram. Sometimes they will overlap, sometimes you will miss, obviously, most of your population because you're doing samples. Now, what's important is that little box underneath. And we're going to see this in a minute. There's a couple of properties right here. Once we take all your samples and we find out the mean of all those samples, we take the total mean of those sample means. It sounds like a tongue twister here. But ultimately, the mean of your samples will be equal to the mean from your population. We'll see that happen. And it doesn't always happen with each sample, it happens over time. Kind of like the theoretical type probability, you have to do it enough times for it to be theoretical. Otherwise, it's empirical until you reach your theoretical. The standard deviation is the thing that will change. And they denote it with an X bar. The X bar tells you it's coming from a sample. So when they write standard deviation, X bar, they mean your standard deviation from your sample. Now when you look in your calculator, your sample standard deviation is your SX. Okay? So to find this is different than the n-1 thing with your SX. To find the standard deviation from your sample means, we take whatever the population was and we divide it by the square root of how many are in your sample. So obviously it's going to shrink down your standard deviation. Say your standard deviation was 10. Your sample size is 25. The square root of 25 is 5. 10 divided by 5 is 2. You went from a standard deviation of 10 to a standard deviation of 2. So do you see your curve shrinking down? Your curve is going to get a lot more narrow. But it's going to still be symmetric about the mean. I know this is a difficult concept, but I want you to be open-minded and try to grasp this. It's tough. Now, here is a good example in your book. But I need you to follow along with me for it. Now, here's a population, 1357. We could put this in your L1, and we can find the mean for this. This is my population. We're going to find the mean to be 4. I add them all together, divide by 4. And in your L1, we can find your population standard deviation to be its radical 5, or about 2.236. This is what your calculator is going to show if you put this in your L1. Right? Okay. That's your population. So we're going to randomly sample 2 of those numbers each time. A sample size of 2 each time with replacement. We have to put them back every time we pick a sample. Otherwise, we would run out of numbers. We wouldn't be able to get too many samples. And we need to make sure that they all have an equal chance of being selected. So we're going to do multiple samples, sample size 2. We're going to calculate the mean of each of those. And then we can put all those means into your L1 and take the total mean of all those sample means and their standard deviation. Yes. Stat, enter. Okay? Now, I want you to see us doing this. Now, what it shows in this, and then we're going to do one as well. It shows in your book, each one of these has an equal chance of being selected. So out of the 1, 3, 5, 7, watch how this pattern works. I select 1, 1. Remember, there's replacement. Then 1, 3. Then 1, 5. Then 1, 7. I did all the ones. This is a possible samples. These are all possible samples that I could get from this. So remember, everything is replaced. So I pick up a 3. I have to put it back in. I get a 3, 1. I want you to see the pattern. 3, 1, 3, 3, 3, 5, 3, 7. Do you see this repeating all the way down with each first number? Right? And then I'm going to do the 5, 5, 1, 5, 3, 5, 5, 5, 7. All the 5s. All the 7s. These are all the possible samples. Of sample size 2 that I could take from that population with replacement. Okay, so far? How we got this? Now, from each one of these samples, you take the mean, the average. You add them together, divide by 2. 1 plus 1, 2, divided by 2 is 1. 1 plus 3, 4, divided by 2 is 4, divided by 2 is 2. 1 plus 5 is 6, divided by 2, 3. Well, because you only have 2 in your sample size, right? Oh. So when you're taking the average for your sample size of 2, you add them together, divide by 2. If we did 5 in our sample, we add them together, divide by 5. Now, these are your sample means. These are your sample means, here and here. Now, if we put those in your L1, and we do a mean, do a calc on this, a one-var stat on this, you should see that your mean from these sample sizes, these are all the possible samples. Now remember, when we do this in reality, we're not obviously going to do all the possible samples, we're just going to take some samples. But conceptually, the mean of your population will be equal to the mean of your sample means. I know this sounds like a tongue twister. It is a tough thing to kind of grasp. So we do this, and we come out with, anybody put this in your calc, in your L1? Well, only these guys. This row here, and continue it with this row. You're still in only L1. You're L1 all the way down. They just ran 2 sections. I put 2 sections back to back here. Like, in other words, it runs down one complete table. Now, once you do this, you're going to find that your mean is the same exact as this. Your standard deviation is the one that's going to change. Your standard deviation is going to say, take the standard deviation from my population and divide it by the square root of n. So our standard deviation up there was square root of 5. Our sample size is the square root of 2. You should get, in your standard deviation, close to this. This is your standard deviation from your sample means. Okay? This is the only thing that's changing right here. We took your curve and we kind of narrowed it down. It used to be a little wider. Here's your 4 right in the middle. This was, well, here's our 4 at the 0. We're still at the 4, but now we're looking more like this. It's still in the middle, but your standard deviation pushed it in. Pushed it in a little bit more. Did you get that?
I got it.
Mm-hmm. So we proved that this works by doing this. So now we're going to do one ourselves because we're still not believing it. Okay? So now I have another population, 135, and I want to take sample size of 3. I want to do a sample size of 3 from my population 135. I want to take all the possible samples. I want to take their mean. I want to take the mean of those means and find the standard deviation. Okay? So this is how we're going to do this. We're going to work this in a pattern. So I'm going to try to fit this whole thing in here. Good. Okay. Now here's your population, 1 through 5. Remember, you're replacing. This time I want my sample size to be 3. So when I do this, I'm going to do all the ones. In other words, 1, 1, 1, 1, 3, 1, 1, 3, 1, 3, 5, 1, let me take out my paper so I get it all straight. 1, 1, 1, you're replacing. And you need a sample size of 3. Okay? Then I'm just going to change the third one. 1, 1. Once you get one pattern, you'll see the rest. 1, 1, 5. Okay, did I exhaust all the things with 1? 1, 1?
Yeah.
So now where do I go? 1, 3, 1, 1, 3, 3. See this last set of numbers going out? 1, 3, 5. That's what I'm repeating over and over. I just exhausted all the 1, 3s.
1, 5,
1, 5, 1.
1, 5, 3.
1, 5, 3.
1, 5, 5.
1, 5, 5. See, we're putting down all the possible samples. And I just, instead of making one big long line, I just made 3 sets of columns. So now, we did all the ones, all the 3, 5 things. So now what do I go to? 3. This whole thing, I did it so now this would repeat with the 3. This would repeat with the 5. Okay? So now, same one way. 3, 1, 1. 3, 1, 3. Do you see it repeat? 3, 1, 5. 3, 3, 3. It's all about finding the patterns in this. Well, obviously, like when we do this, we wouldn't have to find every possible sample, but we are doing it so that you can see what the sample mean is of every possible sample that we can develop and what your standard deviation is. And then we do the same thing with the 5. 5, 1, 1. 5, 1, 3. See it? I'm obviously not going to ask you to do this, but I wanted you to see how this works. Okay, now, to find the mean, you would add them up. I add up 1 plus 1 plus 1, and I divide by 3. So that's going to give me a 1. I'm going to do this all the way down. So I'm going to give you the samples, the sample mean. Because it's divisible by 3, it's not happening nicely. Okay, that's the first row. I should have wrote this in a different color, probably. Nick, while we're doing this, can you put this in your L1? Give us a mean and a population standard deviation? Just these three for now. Just our population one. Okay. So, what's your population mean? 3. What's your standard deviation? 1.63? Okay. Alright, so now, they show us that it's your radical, oh, you gave me your sample standard deviation? You gave me your standard, okay. 1.63. Now, if you take all of your sample means, and you put this all in your L1, we should get the same exact mean as this from your sample means. If anybody wants to be daring enough to do it, you want me, you're okay following this? You should find that your sample means give you the same mean. Remember, these are all possible samples. Don't blow this off, guys. I'm not asking you to do this at any point. I'm just asking you to understand it. I know it's a difficult concept, but if you don't understand the concept, whenever you see the word sample, you're going to forget to do this to your standard deviation. So I want you to see what a sample makes us do. We're proving that this is the same. And we're proving that your standard deviation will now be 1.63 divided by the square root of 3. We're proving, well, I'm rounding it a little bit more. So we're proving that this works the same. So your standard deviation is real close to this. So what we're showing is the mean of the population is the same as the mean of your sample, but what happens to the standard deviation? And what does it do? Get bigger or smaller?
Smaller.
It gets smaller. And it gets smaller so that it brings your curve in a little tighter. So now instead, let me show you the difference. If you had a mean of 3 and a standard deviation of 1.63, and subtract that, so this is 1.37. Now, if you have your standard deviations here, your mean is still going to be the same thing. But look what your standard deviation is going to be, 0.9. So it's a little closer. Your plus or minus 1 is over here. And 68% now sit closer to your mean. Do you see it? It just took this and it made this a little bit more narrow. That's all it did. Made it closer to the mean. This takes care of your standard error of the mean. Because your sampling can give you some possible overlaps and things like that. Did you get that, Nick, on yours? Nick verified this for us. Thank you, Nick, for being our go-to guy. So, my goal